Hello, Math 1341, Calculus 1 students. Here are 4 more problems just to practice before quiz 2. Now, what are the topics for quiz 2? The sections are here. 1.3 is limits and continuity. 1.4 is definition of derivative, instantaneous rates of change, equations of tangent lines. Okay, you can see fantastic things. But 1.3, limits and continuity, part of the material was on quiz 1. And so if you want to focus on studying for this week, limits at infinity, this came on our second day of section 1.3. The notion of continuity came on the second day of 1.3. Also, evaluating limits for piecewise defined functions, just like this. Okay, so we will begin this extra practice for quiz 2 right now. We begin with number 1. We want to evaluate each limit at infinity or show it does not exist. This one, we have polynomial over polynomial. As x grows without bound, the denominator is growing without bound. And the numerator is, well, it's negative, but at least in absolute value, it's growing without bound. So we would have something like this if we think about what's happening. But this is one of our indeterminate forms. So we cannot just address this directly. The way that we did this in class, which is what I recommend, is we divide by the highest power of x that we see, every single term. We have an x cubed, and so let's divide. We would have 2 over x cubed. We would have minus x cubed over x cubed. And then in the denominator, we have x squared over x cubed plus 3x over x cubed. Okay. Each one of these we simplify using properties of exponents. We have 2 over x cubed minus 1, and then we have 1 over x and 3 over x squared. Now, this term, and this term, we can say what's happening. We have a positive power of x in the denominator, so these are all going to 0. Now, how do we address what is happening here? Well, it's kind of this, which is not indeterminate, right? It's minus 1 over 0 is not one of the indeterminate forms, but what it represents sort of in the limit is we have a numerator that's approaching minus 1. We have a denominator that's getting very, very small. So if you think, for example, minus 1 over something very small, 1 over here. This would be a way to think about this. Well, how would we address this? Just invert and multiply the denominator. This is minus 10,000. But now if you keep adding zeros here, you would keep adding zeros here, right, to match. And you can see exactly what this sort of minus 1 over 0 represents. This is approaching negative infinity. So that is the answer here. But that does not exist. So this is a does not exist. For a limit to exist, it means is a finite number. And to say a limit is minus infinity, as I first wrote in this example, it's just a way of saying the limit does not exist. But 1a does not exist as a finite number. 1b, we have another limit at infinity, but it's a little bit different than 1a because it's not just polynomial divided by polynomial. We do have that on the inside, right? We have polynomial over polynomial, but then we have this outside function of the cube root. So let's do this in 2 steps. Maybe my first step, I'll do in gray. First, let's evaluate this limit, the limit as x goes to infinity of x divided by 2x plus 8. Or 2 plus 8x. Very nice. This one is the same strategy as above. The highest power that we see is x to the 1. And so we divide every single term by x. We have x over x. And then we have 2 over x, and 8x over x. Okay, next up is properties of exponents. We have a limit as x goes to infinity of 1 divided by 2 over x plus 8. Now, 2 over x. Well, as x grows without bound, this approaches 0. And so the limit is 1 over 0 plus 8. It's 1 over 8. This is not my final answer because this was just the first step. So now, second step, this is when we actually can find the limit as x goes to infinity of the function I'm interested in here, which is the cube root of x over 2 plus 8x. Okay, cube root is continuous. It's a continuous function. One of the properties of continuous functions is you can bring the limit inside. That's what I'm using here. So this will be the cube root of the limit as x approaches infinity of x over 2 plus 8x. Now, this was what we calculated in step 1. This is the cube root of 1 over 8. And this we can get an exact answer to. This would be the cube root of 1, which is 1, divided by the cube root of 8, which is 2, because 2 cubed is 8. So the limit here, the overall limit, is 1/2. This limit exists and is 1/2. Number 2. Well, in 1b, we use continuity to evaluate a limit, and this question is also a question about continuity. But this asks, for which x values is this piecewise defined function not continuous? And we need to justify or explain our answer. So one of the things that we discussed in class, if you sort of look at any of these independently, so this would be, for instance, if x was strictly less than 1, or on this interval, or x strictly bigger than 1. Well, sitting above those x values, the function's continuous. And the only possible issue would be potentially where you have one function definition on one side and another on the other side, those x values, I call those breakpoints or something like this, because maybe they don't match up to make the limit exist. Or if we had a different kind of piecewise defined function, like in the homework, you could have the limit exist, but then the function value is some other number at that sort of breakpoint. So I will just write, we need to check only 2 x values, which is -1 and 1. And these are the 2 where the function value changes from going from one side to the other. Now, I guess I'll start with x equals -1. To be continuous, maybe I will remind you this up at the top, continuous at x equals a means that the limit as x approaches a of f of x equals f of a. So this is what we need to verify for both these x values. And just like we said, there's 3 parts to this. The limit exists, the function value is defined, and that they're actually equal. So maybe the easier of the 2 is just to evaluate the function first. That we can do. -1 is in this interval, and so I use this formula. F of -1 is -1 squared, which is 1. Okay, now, well, if I want to figure out the limit as x approaches -1 of f of x, I need to look to the left and look to the right. So I will first calculate the limit coming from the left. And second, I will calculate the limit from the right. Coming from the left, this uses values less than -1, but approaching. And that is this formula, which I didn't outline so well. It's here, this formula. Coming from the left, we see the limit would be minus 1 squared. We evaluate the top formula and we get 1. Coming from the right, we use values bigger than minus 1 and approaching. And this would be here. So to get the limit from the right, we just evaluate 2x minus 1 at negative 1. We get 2 times minus 1, which is negative 3. Well, you see, here's the limit from the left, here's the limit from the right, and these are not equal. So the overall limit does not exist. Immediately, we know that f is not continuous at x equals minus 1 because the limit does not exist. Now, let's check the other point, which was at x equals 1. First, let's calculate f of 1. Well, 1 is here. It's in this interval. And so f of 1 is the square root of 1, which is 1. Now, we move on. We calculate the limit as x approaches 1 from the left. We calculate the limit as x approaches 1 from the right. And it's very similar to before. From the left, we look at values less than 1, but approaching. And so we will be evaluating this formula at 1, 2 times 1 minus 1. This is 2 minus 1, which is 1. This is the limit from the left. The limit from the right, we use values bigger than 1, but approaching. And so we evaluate here. This is the square root of 1, which is 1. Oh, this is looking great because you see the limit from the left equals the limit from the right. And they're both equal to 1. So the overall limit exists and equals 1. Okay, well, this says that f is continuous at x equals 1 as f of 1 equals the limit as x approaches 1 of f of x. That is the definition of continuity at that point. So the answer, well, maybe I'll put it down here. The only value where the function is not continuous is here at x equals minus 1. This is our answer. And this is the end of number 2. Now we have a definition of derivative problem. We want to find the instantaneous rate of change of this function. F of x is the square root 2x plus 7 at x equals 1. And I'm supposed to use the definition, and I even give it to you here. So we had a difference quotient on the last quiz and also on the last quiz practice. This is a little bit, maybe a little bit more involved function, but the algebra of difference quotients, as you're likely aware, can be a little bit tricky. So it's very good to practice and practice and practice, and then you will have it down, I am sure. So the first step, I will start here with f of 1 plus h minus f of 1. Step 1, evaluate f of 1 plus h. Everywhere you see an x, we put in 1 plus h. So it's like this, and then plus 7. Okay, then subtract off f of 1, which is the square root of 2 plus 7, which is the square root of 9. Now I want to take one more step here. This first square root, you see, this would be 2 plus 2h, and then plus 7. So altogether here, I have a 2h plus 9, and then I have minus 3. Okay, this is quite likely the place where more than one student will get stuck. But there's certain tricks that the more you practice, you can just be prepared for. One of them comes when you see, just like this, a difference of square roots. And as I mentioned in class, it's a trick that you learn. It's called rationalizing the denominator. Of course, there's no denominator here, but that's where this comes from. So what we do is we multiply by square root 2h plus 9 plus 3. And then, of course, I can't just multiply by that alone. That would change it. So you multiply by 1, but written as square root 2h plus 9 plus 3 divided by square root 2h plus 9 plus 3. Okay, I have multiplied by 1, but I've done it in a way that I will no longer have this square root in my numerator. Okay, so when I multiply, the firsts become 2h plus 9, and then you notice outer and inner, they add to 0. That's why this works so lovely. And the last, I just multiply, minus 9. And then I have this denominator, which is the square root 2h plus 9, and then plus 3. Now this is looking so wonderful. We have 2h divided by the square root 2h plus 9 plus 3. This is h times something, right? This is h times something, and that's exactly what I want. So I can divide by h in the next step. So I have f of 1 plus h minus f of 1 divided by h. All that happens is, maybe I'll do it in 2 steps, but this is when everything gets wonderful. By h. And this h is in the denominator. H times all of this. Square root 2h plus 9 plus 3. Now you see we have left something that is defined at h equals 0. And so I can just take the limit just by evaluating at h equals 0. So the derivative evaluated at 1 is a limit as h approaches 0 of, maybe I'll just copy this and paste because I have simplified the difference quotient. And you see we get 2 over the square root of 9, which is 3, plus 3. This is 2 over 6, or 1 over 3. This is the instantaneous rate of change of this function at x equals 1. It's also the slope of the tangent line at x equals 1. Is also the derivative evaluated at x equals 1, right? That is all of these quantities, but this is the end of number 3. Now, just like I was mentioning, this quantity is the slope of the tangent line to y equals f of x at x equals 1. And the very next problem on our quiz practice involves equations of tangent lines. Number 4. Well, we have 2 parts here. And because we have not talked about all the rules for derivatives yet, both of them, you'll notice I give you information about the function, and I also give information about the derivative, and that helps us complete the problem. So in part A, we want the equation of the tangent line to this function at x equals 2, and we can use that the derivative evaluated at 2 is 12. So both A and B are quite short problems since we have this extra information. First of all, we have a slope, which is the derivative evaluated at 2, and we're given this is 12. And then we have a point. Anytime you have a slope and a point, you can write down the equation of a line. The point will be 2 comma f of 2. And so I need to evaluate the function at 2. This will be 3 minus 4 plus 4 squared. This is 3 squared, which is 9. Okay, so the point here, which is on my graph, and it's also on my tangent line, is 2, 9. Now let's write down an equation. Would be, say, y minus 9 is 12, x minus 2. You can leave it like this. You can also put this in slope-intercept form. Maybe I will, because I know some people like slope-intercept form. So what do I have here? I have y is 12x minus 24 plus 9. This gives me 12x minus 15. This would be another option. Either one is perfectly fine as a final answer. Letter B, we are given the derivative. Okay, this is important. This part is the derivative. It is not the original function. So we're given a formula for the derivative, and then we're also given the original function evaluated at 1 is 3. We want to find an equation of the tangent line to the original function, f of x, at x equals 1. Okay, well, it's very similar to the above, except we just have different information. So we know the slope. This would be the derivative evaluated at 1. And we know a point on the line, also on the graph of the function, is 1 comma f of 1. Now, let's look at what we're given. We're given f of 1 is 3. So a point on my tangent line is 1 comma 3. And then the derivative at 1, we have a formula, is 1 plus 1 cubed, which is 8. 2 cubed, which is 8. So we just have y minus y1 is m x minus x1. This is one answer. Or you could also, just like before, you could put it in slope-intercept if you choose. We would have y is 8x minus 8 plus 3. We have y is 8x minus 5. This is another way to leave your final answer. Either one is perfectly fine. Thank you, everyone. This has been extra practice for quiz 2, and good luck on the quiz this week.